So the next talk of this session is by Prabha on quantum error correction in near-term quantum processors.
Thank you, Uma. Thanks to the organizers for having me here for this very interesting meeting. And thanks also for very thoughtfully scheduling Himadri and myself in the same session. And thanks to Himadri for covering a lot of ground in introducing quantum error correction. So you will find I will just skip through some of my slides, and that gives me time to talk a bit more about my own results. Because what I'm going to talk about is a slightly different notion of error correction. Of course, the ideas, basic ideas are the same, but then we would like to extend this framework now beyond what Himadri has already outlined, namely the so-called Knill-Leflam conditions, or what I will often refer to as the perfect error correction conditions. And I would like to show you how, if we try to go beyond this framework, somewhat restricted framework maybe of perfect error correction, one could allow for more efficient quantum error correcting procedures, which perhaps could be of more use or more amenable to implementation in today's what we often refer to as these noisy intermediate scale quantum devices. So yeah, I'm from IIT Madras. I'm part of the Center for Quantum Information, Communication and Computing. And the work that I'll be talking about is actually with two PhD students of mine, Debjyoti and Saurabh. So we all don't, I mean, I guess today I don't need to talk about the need for error correction, but I just want to point out that this was, of course, said in 2018, and today we are not very far away, actually. Instead of 100, maybe we are talking about processors with 500 qubits, no matter which platform one looks at. Unfortunately, we are still limited by noise. And this is noise not just in the qubits, it is not just the qubits undergo decoherence, but it's also that the operations that we would like to do on them in order to realize useful quantum computing, these operations, which we call quantum gates, are also noisy. And so we believe that quantum error correction, and in addition to that, I should also mention fault tolerance, that these two frameworks are the reason that we think that we can actually extract the capability that we want from these kind of quantum processors. And in the morning, we saw some very nice use cases of quantum processors for simulating many-body physics, whether it's in quantum field theory or in condensed matter systems, right? So this is just a quick snapshot of what one means by NISQ and what one means by eventual universal fault tolerance quantum computing. So we are here today, right? We are still somewhere between 100 and 1,000 qubits. And this error probability is what I'll talk about for the rest of my talk, and I will also talk a little bit about the threshold in the end. So we are today limited both by the number of qubits that we have and also by the degree of noise that we're able to guarantee in an experimental setup, right? So we are not yet sort of below this error threshold, and so if one wants to now scale up to implement the kind of error correcting schemes that one often hears about, and also to implement fault tolerant quantum computing, then you see that you're all the way at something like 10 to the 6, 10 to the 7 qubits. And we heard actually in a talk yesterday that if you actually want to think about doing this on using topological quantum codes, then Julian Vidal told us that to think about 2,000 qubits and to think that they are all going to be topologically protected, maybe a tough ask, right? So here's an example of what is the state of the art today. So this is Google's surface code. This is what they call a distance 7 surface code. The distance of a code tells you the number of errors that the code can protect against. So in Himadri's talk, for example, he spoke about protecting a single errors, but a distance 7 code would mean that you can actually protect on errors on up to 3 qubits, right? And but however, you still only have one logical qubit with 107 physical qubits, which are arranged in a lattice like this. This is what is called a surface code, and these are the kind of stabilizers that one measures and so on. I don't want to get in the details of this, but just to show you the sort of lattice systems that one is thinking about in order to implement these surface codes, or more generally topological quantum error correcting codes. So let me now back up a bit and go back to the basics, since I'm going to talk about extending this framework of quantum error correction. So why are these qubits so noisy? Well, because they are not truly isolated systems, they interact with an environment, and this interaction with the environment is not something that you can completely model as a unitary dynamics on the system. You have to move beyond unitary evolution on the system, and you have to talk about what are called completely positive trace-preserving maps. So this U would be some joint system bath unitary. I trace out the environment degrees of freedom because I'm only interested in manipulating the system degrees of freedom. And then when I trace this out, I end up with what is called a dynamical map on the system states alone. And there is a nice description of this dynamical map in terms of a set of operators. I just call them Krauss operators for short, but Choi, Sudarshan, Krauss operators would be the right name for this. And so you can now model the system evolution via this map. So I start with some initial state, and then after a certain time, the state of my system has evolved to this, where the evolution is now governed by this set of operators called the Krauss operators. There's nothing special about these. They are not unitary, they're not Hermitian. They could be any old operators. The only constraint that they have to satisfy in order for this to qualify as a valid physical evolution is that they must satisfy the so-called trace-preserving condition. And this is to ensure that your conserving probabilities, your states are normalized in the end and so on. So here's an example of this abstract framework that I wrote down. So this is your transmon qubit architecture, or at least one example of a superconducting qubit architecture. This is your standard quantum harmonic oscillator, but this is an unharmonic oscillator. And what one does in superconducting qubits is one addresses the ground and the first excited state of this unharmonic oscillator. Now, if I were to abstract out the details of this, this essentially mimics a two-level atom in a cavity. Right? The physics of this can be modeled via the Jaynes-Cummings interaction, and that's the kind of system bath interaction that I was talking about. But I'm now interested only in this two-level atom, so I trace out this cavity degrees of freedom, and what I end up with is one such quantum dynamical map called the amplitude damping channel. So maybe I should just go back to this and point out that it is precisely because these EIs are non-unitary that I have noise or decoherence on the system. If I had just a single Krauss operator, that will necessarily be unitary, and then all I have is unitary dynamics, which is reversible. But now that I have this operator sum form, this is no longer reversible, and hence sort of the origin of noise and so on.
Trace-preserving condition.
Yeah.
Is that just for the equality or also for the...
So the inequality is to tell you that this should actually be trace non-increasing. So something that is trace increasing would be unphysical. Something that is trace decreasing is okay. Yeah, it should, yeah. So yeah, I kind of brushed under the carpet. So something that is trace decreasing, I can always normalize and make it trace preserving. Yeah. Is there another question? Okay, yeah, sorry, I should have, yeah. Right, so what I demand is actually that it be trace non-increasing. Yeah. Okay, so here's an example, and there's a reason why I showed this example, because this is a very natural noise process in physical systems. What do these two matrices actually do? So if I think of this as my qubit, this is my ket0, this is my ket1, then the first operator actually is not very problematic, but the second operator actually pushes the excited state to the ground state with the loss of a photon, emitting a photon in the process, right? And the probability for this single photon decay process to happen is what this gamma captures for me. This gamma is also what we in the quantum error correction community would call the noise strength, because the larger the gamma, the larger is the probability that your state is going to decay down to the ground state. So this is an energy dissipation process, and this is a very natural source of noise in most quantum hardware today. And of course, this gamma you can we model as a function of time, in the sense that you imagine that I prepare my state in some superposition, and then I do something else, but in the time that I do something else, the noise kicks in, and then with time, increasing time, I'm more and more likely to just have damped down to the ground state in this process. And this decay factor here, this T1 in the exponent, is what we call the coherence time of the qubit, right? Now, I just wanted to show this here because I thought maybe of interest to some of the audience in this community, that amplitude damping also occurs in spin chain systems. So this is a very old paper of Saugata Bose, where they actually talk about quantum state transfer on spin chains. And this is somewhat analogous in a sense to what Abhishek was talking about yesterday, where you had this set of fermions, and then you were treating part of this set as the bath, right? So here again, you have a single spin here. You would like to transfer this information out to a different spin here, which I call the receiver spin. And the way I would like to transfer the state is via the natural Hamiltonian evolution of the system. So if I were to restrict my attention to these kind of spin-preserving Hamiltonians, and this is simply a 1D ferromagnetic spin chain Hamiltonian, then this single spin, and then I have to read out the information here. So I trace out the rest of the spins here. So that effectively acts as my bath. And then this state of this receiver spin, although I started out with a pure state here, is going to be in a mixed state. And that mixed state can actually be described via a map that looks exactly like amplitude damping, with the noise probabilities or the gamma actually now being represented by the transition amplitude. So in a sense, it's actually an amplitude damping noise with the complex gamma parameter, right? Unlike the Jaynes-Cummings where I actually get a real, the gamma is actually a probability, right? In this case, I have to make mod squared of this or a modulus of this to get a probability out of this, okay? So, so we did some work here where we actually showed how you could improve the fidelity of the state transfer by modeling this as an amplitude damping channel and then doing error correction on this. So I just referred to that work here. Okay, so this kind of noise model that I'm talking about is not what one often encounters in discussions on quantum error correction. Rather, one talks about bit flip and phase flip noise, right? So these are what I refer to as Pauli noise channels, because these are noise models where the Krauss operators are essentially just Pauli operators. And the reason that this is noise is because you now have a probabilistic mixture of identity or X happening. If you just had X, that's not noise, right? So it's a probabilistic mixture of actually a pair of unitary operations. So Pauli noise is, of course, well studied. You have, Himadri spoke about the classical case where you can think of bit flip. In the quantum case, you can also have phase flip, and then you can put these together and come up with a depolarizing channel and so on. So in the next few slides, I'm actually going to talk about the so-called framework of standard error correction. I'm going to talk about this very quickly since Himadri already spoke about it. But I'm going to then move on to talking about non-Pauli noise, like amplitude damping noise, and talk about how one can design error correcting protocols for non-Pauli noise, okay? So the only new thing in this slide, which Himadri did not mention, is this nice error correction sonnet. So I just want to talk about this. With group and eigenstate, we've learned to fix your quantum errors with our quantum tricks. So I'm just going to show you in the next couple of slides what group and eigenstate are. That's obviously referring to the stabilizer framework. So yeah, we discussed the no cloning theorem and all of that, and we spoke about going from physical qubits to encoded qubits, the idea of errors having to distinguish. The idea of the reason that you do this encoding is because you would like to distinguish the action of different errors on your code space. And you say that something is a good error correcting code if you're able to distinguish the action of these different errors, right? So this was also discussed. And of course, there is always a threshold, right? If this probability of bit flip was greater than a half, then this entire scheme is not going to work, right? The reason that this works is because you put a threshold and say that if my probability of bit flip is smaller than a half, then I know that single qubit errors are more probable and this whole scheme works, okay. So this is a kind of schematic of what error correction is. So again, I'm going to skip this. I'm just going to point out that there are 2 degrees of freedom that I have in choosing an error correction scheme. I can choose the encoder, which is basically choosing the code space. So in this case, I chose a 3-qubit code space. Now, a 3-qubit space, of course, has many more states, than just these 2. But I have decided to encode my information into this particular subspace of the 3-qubit space. So that is the choice of encoding that one has. And the second degree of freedom that you have is choosing the decoder, which I'm going to use synonymously with the recovery map. In the case of the 3-qubit bit flip code, the recovery here, this is the second part of this circuit here, is basically, again, this was explained in the previous talk, but so I just want to point out that this recovery here comprises entirely of unitary operations. So these are C naughts that you do with an ancilla. You measure the ancilla, and then you go back and apply X operations again on your so-called data qubits. So it's entirely composed of measurement and unitary operations, right? So I'm again going to talk about how you can extend that a little bit. So for Pauli operator errors, so this is what I was just mentioning. The recovery operation is simply the inverse of the noise operator because your noise is simply unitary, okay? Right, so not sure if I want to discuss all of this, but maybe just a little bit to talk about the idea of what a stabilizer is, since we are at this juncture of talking about Pauli noise and so on. So the standard framework of error correction says that you can decompose all arbitrary noise, even if it's of the amplitude damping form, into Pauli errors, right? And Pauli errors obviously belong to, they are part of this n-qubit, this group of Pauli operators on n qubits, right? And then I pick an abelian subgroup of this n-qubit Pauli group, and I pick a set of states which are stabilized, means which are left invariant by this abelian subgroup of the Pauli group. And this is exactly what gives me the stabilizer group, and then the stabilizer code space, which is basically the vector space which is left invariant by the stabilizer generators. So in the example that we had, that's at the bottom, so the 3-qubit bit flip code, these are the two stabilizers for the code, right? Now, what are the errors that can be corrected by a given stabilizer code? Well, that is simply the any error which is not, any Pauli operator which is not in the normalizer associated with the stabilizer is an error which can be detected and corrected by the code, okay? So this sort of is a very, very 2-second summary of the stabilizer framework. And then this, of course, gives us some very nice things like the so-called toric code and so on. So maybe I will not dwell on this much, except to say that today what most groups try to implement in terms of quantum error correction is indeed topological codes of this form, which are essentially stabilizer codes, means the error operators that they consider are X and Z, and then they design syndrome extraction procedures for X and Z errors, and the specific variant of the toric code that is often implemented is the so-called surface code, and I showed you this picture at the beginning of Google's surface code implementation, right? But quantum states, as I just explained using a couple of physical examples, it's not just Pauli noise. So what does one do when you have noise like amplitude damping? Well, the answer is discretize all errors in terms of Paulis. So for example, with amplitude damping, you can write down the no damping operator like this. It's a combination of identity and Z. You can write down the single damping operator as a combination of X and Y. And so essentially you have a model which can be broken down into a combination, a linear combination of Paulis. And so you continue with your stabilizer framework, you correct for X and Z errors, and then by linearity, you correct for non-Pauli noise as well. So that's what standard framework of error correction tells us. But then this puts some constraints on the size of the code and its error correction properties, right? And one such constraint is the so-called quantum Hamming bound, which says that the shortest code that you can design to protect a single qubit requires 5 qubits. Now, a while ago, people noticed that instead of doing this whole stabilizer error correction, if you actually tried to directly correct for amplitude damping noise, you could actually design codes that beat the quantum Hamming bound. You could come up with, for example, a 4-qubit code, which corrects to the same degree as a 5-qubit code, and I'll tell you what I mean by that. And so then it seemed like there was some payoff to actually designing codes which are tailored to specific noise models, where one knows that your physical hardware is dominated by this kind of a non-Pauli noise, okay? So that's sort of the whole idea of noise-adapted quantum error correction, that can one actually design more efficient error-correcting protocols by looking at noise models which are physical in origin, unlike bit flip and phase flip, which are more artificially constructed, and what kind of codes and recovery maps do we have to do in that case, okay? So how do I benchmark? So I said that this 4-qubit code achieves a similar degree of performance or similar degree of protection as the 5-qubit code. How does one benchmark these things? Well, one uses a fidelity function. So this is simply my E represents the noise map, the R represents a recovery map, and this is the final recovered state after error correction. This is the initial state. I simply take the overlap. But now remember that I'm doing all this in an encoded space. So if I want a sort of guarantee that this encoding scheme is going to protect me to this degree, then I need to minimize this over all states in the code space, and that gives me what's called a worst case fidelity measure. This is something that we'll use to benchmark the performance of our noise adapted codes. So again, just to emphasize, the recovery map the example that we saw with the 3-qubit code, the recovery is very structured. It's a syndrome measurement followed by a unitary operation, but it need not be so, right? Physically, I'm allowed to do any completely positive trace preserving map, and I'm allowed to design any such completely positive trace preserving map as my recovery map. So that is one way in which we'll broaden the scope of what we can do. Now, along with noise adaptation comes another concept, which is that of going beyond perfect error correction. So the scheme that we saw, which is the 3-qubit code and so on, or the scheme that we saw in Himadri's talk, says that you can perfectly correct for a particular subset of errors, right? So in this very formal language, what this means is that for any density operator on the code space, after the action of the noise and the recovery, I exactly get back to the state, the initial state that I started with. But now I would also like to tweak this definition a bit and say that I only demand approximate error correction. So I say that my code is approximately correctable for some noise if the final state that I get after the action of noise and recovery is not exactly rho, but it's close to rho. And by close, I mean close exactly in this fidelity function. So for all states in the code space, I have a fidelity which is close to 1, or it is of the order of 1 minus some very small parameter epsilon. And this epsilon is something that I could set as a threshold to now design these kind of approximate quantum error correcting codes. So now Himadri already spoke about the kind of conditions that we need, algebraic conditions, in order to demand this perfect error correction, right? So here's a pictorial representation of this, which I think was also shown. So what this says, well, I have encoded my information in some subspace of a larger Hilbert space, and then I have all these different Krauss operators or noise operators, and they map my code space to different parts of this larger Hilbert space. But so long as I ensure that they map them in a way that is non-overlapping, but not only is it non-overlapping, also these errors are just unitary transformations. Each error operator is just a unitary transformation of the code space. So if I can ensure both these things, then I have perfect error correction. And that is what is captured by this algebraic condition. But now if I relax that and I look at more general scenarios like this, I could think of mathematically, again, adding a perturbation to this algebraic condition, and now say, what if I think of code spaces? So of course, I realize that this is not the form in which Himadri wrote this down. So this P here, I should tell you, is a projection operator. So the P is a projection onto the code space. EI and EJ are error operators. Lambda IJ are just some scalars. So what if I now say that this algebraic condition can come with an additional noise term, which is some other operator delta IJ times P, and this delta IJ essentially captures all these overlaps. It tells you the degree to which you're unable to distinguish your different error syndromes, and it also should capture the non-unitary deformation of your code space. So both of this is somehow encapsulated in these operators delta IJ, and these kind of conditions are what we call approximate quantum error correction conditions. Yeah. No, lambdas are scalars and deltas are operators. So the left-hand side is an operator. What the standard or Knil-Laflamme conditions tell you is that this operator must be equal to some scalar times the projection on the code space. So what this is saying, for example, if I was equal to j, it's telling you that each error operator, the action of each error operator on the code space is just a scaling of the code space in some sense. So I can now sort of do a polar decomposition and see that each error operator is simply a unitary on the code space. But here I'm saying that this is some general matrix of which lambda is just a leading term, and this additional operator is a perturbation of that. Yeah. Go ahead. So right now I am still at the physical level, right? I have not even gone to the logical level because the EIs and EJs are my error operators. Okay, so I should take that back. So my EIs and EJs are error operators on the code space. So your question is, how do I, yeah. the delta ij are not necessarily just rotating the code words. They could be any, so if in particular, for example, they will be off-diagonal matrices. Okay, so what I'm saying is if my P, EI dagger, EIP, according to this condition, should just be this, which would just be something like this. So this is the perfect case. But now I'm saying that more generally it is this plus something else, okay, which of course has support on the code space only. But there are now terms here which are suppressed in the noise strength, but there is this additional term. I hope that. You don't know, no. It could be anything, yeah. So that just comes for free, right? Because what's on the left is Hermitian, so lambda ij has to be, yeah. Need not be. It could be anything, yeah. In general, it could be anything, yeah. Okay, so there are several versions of these kind of approximate quantum error correction conditions. Maybe I should put some references here, but so this is now the framework that we'll be looking at, because when one starts talking about these kind of non-Pauli noise, you can no longer come up with these kind of perfect constructions which are nicely going to map your code space to distinct parts of the Hilbert space. You may or may not, so we'll see some examples. But this will be the more general scenario in which you can talk about both approximate as well as noise-adapted quantum error correction. So here's an example. So here is 4-qubit code. So this is the 4-qubit code example that I spoke about earlier. So these are the two code words. This is a code that is tailored to correct for single qubit amplitude damping noise, which means I'm now in this 4-qubit space, but I'm only looking at errors which affect 1 qubit at a time. And for all those single qubit damping errors, this works as a good quantum error correcting code. Notice that this code is also stabilized by a Pauli group, right? But then I just told you that you may have to move out of the stabilizer framework and so on. Well, what you have to move out of is actually the fact that just measuring these stabilizer operators no longer suffices to distinctly identify the error syndromes. So again, this was something that was emphasized in the previous talk, that you have to be able to distinctly identify these error syndromes in order to design a perfect error correcting code. But now that we've relaxed that constraint, we can admit these smaller codes which do have a stabilizer frame, a set of stabilizers that you can associate with them, but just measuring this set of stabilizer operators is not sufficient to guarantee error detection, unlike in the standard stabilizer framework. So in this case, the way we deviate from standard error correction is we still preserve the fact that you're mapping to non-overlapping spaces, but they are no longer unitary transforms. So I'll come back to this later again. So what happens when we go to codes like this is that you have to do non-trivial recovery operations, which means you have to measure not just the stabilizer generators here, but you also have to measure sometimes secondary syndrome or non-stabilizer operators. You may have to make measurements. For example, in this case, you have to make a single qubit Z measurement in order to identify the exact location of the damping, right? And that single qubit Z operator is not in the stabilizer. It in fact anti-commutes with the X stabilizer. So, and also you have to extend the scope of your recovery maps from beyond just unitary operations to more general CPTP maps. And in terms of performance, this kind of a 4-qubit code achieves a fidelity which goes as 1 minus something gamma squared, which is similar to what a perfect, the so-called perfect 5-qubit stabilizer code will do. I just want to point out here that if you remember, gamma was the probability of the single photon process, that the probability of a single damping error. So you say that you have succeeded in your error correction if you have gotten rid of that gamma term in your fidelity expression, right? What this means is you have corrected for all the single damping errors. There are some remaining 2 damping errors, but that is the case even if you use a 5-qubit stabilizer code. So you've effectively reduced your resources and you've achieved the same level of fidelity, okay? Right, so now you can sort of play this game and you can say, is that the only 4-qubit code that one can come up with? So we showed in using a numerical procedure, using this framework of approximate quantum error correction, using these kind of conditions and so on, that you can actually there are many such 4-qubit codes that you can actually construct. So this is one such example of that, right? So this pink one is a 4-qubit code. The dark blue line is your 5-qubit stabilizer code. So we in fact have codes that achieve better fidelity than the 5-qubit code. So what's on the x-axis here is the noise strength, what's on the y-axis is fidelity, and the linear line here is this is basically the raw qubit or the unprotected physical qubit. So this is how the fidelity would drop off as 1 minus gamma. Remember, I'm doing the square of the fidelity, so it would drop off as 1 minus gamma, whereas it should drop off quadratically in gamma if you have error corrected the qubit, okay? Okay, so how did we actually wind up with these other 4-qubit codes? So this example that I showed you was of course constructed analytically, right? So how did we wind up with these kind of codes? Well, you can pose approximate error correction, or quantum error correction in general is an optimization problem, right? You can say, well, what is the best recovery? So remember I told you there are 2 degrees of freedom that you have. You have the code and you have the recovery. And you can ask what is the best recovery and the best code which achieves the best worst case fidelity. And you can sort of fix a dimension. You can say, I want to think about a single qubit, encoding a single qubit in so many qubits, and you can ask what is the best code and what is the best recovery, right? But this is, as you can see, a horrible optimization problem. It's a triple optimization problem. And especially if you want to think about doing this for worst case fidelity, it's a very hard problem. You could think about alternate measures of fidelity, like average measures of fidelity and so on, which would make it numerically more tractable. But in general, this is a hard problem because you have to do this 2-fold optimization. Maybe you fix the code, you optimize for the recovery, and then you fix the recovery, and then you optimize for the code. So you can sort of, there are variants of this that people have done. But what I want to talk about in the next 8 minutes or so that I have is some analytical answers to this, right? So one of the things I want to talk about is an analytical solution for the recovery map, where we show that there exists a near optimal universal construction for a recovery map, and this goes by the name of the PETS map, and that this can recover with good worst case fidelity for arbitrary noise and arbitrary codes. And more recently, with my student, we came up with quantum circuits that can actually implement this recovery map. Remember, I told you that we go beyond measurements and syndrome measurements and unitaries. So now my recovery itself has become a completely positive trace preserving map, which is a valid physical operation. So I should be able to come up with a quantum circuit for that. So that's one direction that we pursued, and we came up with some nice quantum circuits for the PETS map. Now, you can also ask, going beyond qubits, what about qubit codes for amplitude damping? So we showed, in fact, that there are 4 qubit codes for amplitude damping. So no matter what the D is, no matter what the local dimension of your space is, you can construct these 4 qubit codes. So you only need 4 of them to protect against single damping errors, no matter what the dimension is, right? And much more recently, interestingly, we answered a question which was posed very early on in one of these papers about whether there could exist a 3-qubit code for amplitude damping noise, and we answered very positively, and we showed that there can exist a 3-qubit code, provided, again, you expand your framework of recovery and you allow for what we call post-selected or probabilistic recoveries. So I'm not going to have time to talk about all of this, so maybe I'll talk a little bit about the first 2 and the third one some other time. Yeah. Okay, so what is this analytical solution? I want to talk about this a little bit because I think this is of interest beyond just quantum information now. So for any CPTP map or any noise channel and any code, I can write down a set of operators like this. So notice that these are simply the EI dagger is simply the adjoint of the channel operators. The P is a projection on the code space. But what I have out here is a somewhat complex object. That is E of P to the minus half. So P is, remember, the projection on the code space. So in a sense, this is a state which is capturing on average what the noise does to your code space. And then you need to do some kind of pseudo inverse of that. But this set of operators, it turns out, forms a valid quantum channel, meaning it satisfies your condition of being trace preserving, in fact. So this quantum channel is what today goes by the name of the PETS map. And what we showed in our work is that this PETS map is in fact the standard stabilizer recovery that you write down if this code is a perfect error correcting code for this noise map. So we showed that in the limit of perfect error correction, the PETS map is your standard recovery map. And for any other pair where your code is not perfectly correcting, means it does not satisfy the perfect form of the Knill-Laflamme, but it satisfies some approximate form of the Knill-Laflamme condition, then the PETS map achieves a worst case fidelity, which is close to that of what could be an optimal recovery channel. So means we took the PETS map, we came up with an analytical expression for its fidelity, and we proved two-sided bounds on that, which showed that it is always close to optimal. You could have a much more optimal recovery map, but your PETS map would do no worse than some factor times whatever is the noise strength up to which your optimal map is correcting. And so we can then also rewrite the perfect error correction conditions directly in terms of the PETS map and get approximate error correction conditions. So this I'll come back to again. So I just want to point out that the PETS map today has used beyond just AQEC. So for example, there are continuous variable extensions of the PETS map. There are some connections of approximate error correction with ETH and translationally invariant systems. And I also want to point out that today the PETS map also finds a lot of resonance in the ADS-CFT literature, where it is thought of, again, in a similar context, as a universal recovery map for bulk reconstruction. And we reviewed this a little bit in this review article that I co-wrote a couple of years ago. So now I'm going to talk about the PETS map being this abstract CPTP map. How is it really useful for quantum error correction? It's fine that we proved fidelity bounds, but can it be actually implemented on a quantum circuit? So let's look at this map a little bit closely. So this map, as I pointed out even there, it's basically comprised of Krauss operators of the form EI dagger. Now for any general noise channel, the adjoint channel need not be physical. Means if I take, for example, the amplitude damping noise, I consider the adjoint operators, they are not going to form a trace non-increasing map. They're going to form a trace increasing map. So what the PETS map essentially does is it says that the adjoint map is the correct answer for error correction, but the adjoint map is not always physical. So let's add a few things to make this physical, and that's essentially how we think of the PETS map. So you're adding this E of P to the minus half, essentially to make this trace increasing map to become a trace non-increasing map and to make it physical. And then, of course, you project back to the code space because that's what you would like to do in any error correction procedure. So viewed like this, now it looks like implementing this physically is not really feasible because this first map here is not a physical map. So how does one do this? So what we came up with is do not decompose the PETs like this, but instead look at it as a CPTP map and think about doing an isometric extension of the CPTP map. So maybe I'll just go to this. So in this work, we demonstrated 3 different ways in which you can construct quantum circuits for this CPTP map. One, you can just do what's called an isometric extension, which means you have your map, which is a dynamical map on the system, but now you do the reverse of what I showed you in my very early slides. You add additional ancillary qubits, and you realize this dynamical map as a unitary on a larger system. It's what's called the Stein spring dilation or an isometric extension, and it turns out that that gives actually a much more efficient implementation of the PETS map than what was done a little bit earlier using a different approach. We also show that any CPTP map can be realized as a sequence of measurements. These are not projective measurements, but these are this class of POVMs. So that's another approach to implementing it. And we could also tweak this algorithmic approach a little bit and get a slightly more efficient implementation. So you see in all of these, we kind of improved the exponent by a factor of 2 in the implementation that existed prior to this. So I will skip all of this since I'm out of time and just show you some results out here. So this, now that we have a circuit, well, we can actually take it to a quantum hardware and maybe try and simulate this. So these are some simulation results for these PETS recovery circuits from the IBM hardware. So this is a simulation, but it's a noisy simulation in the sense that we inject amplitude damping noise in the system, and then we ask what happens when there is no error correction and what happens when we do the PETS recovery. You see that doing this PETS recovery circuit actually keeps your fidelity above 0.95, whereas here you're actually going to decay off So this, of course, is your the ket 0 state, which is the fixed point of the amplitude damping map. And this is, of course, the ket 1 state, which is going to get completely damped to the ket 0 state. But of course, on real hardware, when we try to do this, then we end up with somewhat bad fidelities. And this goes back to the very early point that I made about the gates being noisy. The error correction procedure involves a lot of gates. It involves encoding, it involves this recovery circuit. And when all of these processes are noisy, then that brings down the fidelity of the procedure in an actual hardware. So I think I'm going to just jump off to right. So I just want to conclude with this. So this is, like I said, some very recent work where we use this framework of approximate quantum error correction, and we showed that there exists a 3-qubit code for amplitude damping, which actually performs much better than the 4-qubit or the stabilizer 5-qubit code. Of course, we had to, again, go beyond the framework of standard error correction, in the sense we had to implement a probabilistic or a post-selected recovery. But essentially, our scheme tells you that either you know that the noise occurred and then you have corrected for it with high degree of fidelity, or you know that it was noisy, but your error correction procedure failed, so you discard this instance of your protocol, right? So that's what I mean by a post-selected or probabilistic protocol. So let me, yeah, I did not have time to talk about fault tolerance, so let me just go off to my, so I became ambitious because I thought after Madri's talk I would have more time, but right. So yeah, so I hope I've convinced you that noise adapted error correction can provide a good degree of protection from the dominant noise process that affects physical qubits. The standard schemes, as we saw, stabilizer codes, topological codes, etc., are rather resource intensive. So these can be more resource efficient. So are they more suited for NISQ era? But going beyond that, so these are this is the main result that I think I showed you. This I could not show you in detail. But the question is, can one actually go from these kind of noise adapted codes to something which can actually be fault tolerant? And we do have some recent work along this line. But a fruitful line of investigation could be to develop smaller noise adapted codes at the physical level and then build general purpose codes on top of that to realize a fault tolerant architecture. So, thank you. I'm happy to take questions.
Thanks, Prabha. So, questions?
Any particular reason you just studied amplitude damping channel? Why not other Pauli?
So, like I said, for Pauli noise, the stabilizer framework works beautifully, right?
I see.
So, for Pauli noise, we have the stabilizer framework. So, incidentally, with Pauli noise, also people have looked at what is called biased noise, which means you have an architecture where you know that the Z noise is effectively killed and your dominant noise is X noise. So, you can then design codes which are obviously shorter and tailored for that. But these are still within the domain of Pauli noise, right? Whereas something like amplitude damping, which is physically sort of a well-motivated noise channel, is not really studied directly, right? So that's the reason it makes for a kind of classic candidate for these kind of noise-adapted procedures.
So another point you make, no, this adjoint channel is not a physical thing.
Yeah.
Because this is happening due to this, what is called this? Your study, this amplitude damping is a non-unital.
Correct, yeah.
For unital, adjoint will always be a valid map.
Absolutely. So that's in fact the reason that the PETS map is the same as your standard stabilizer recovery map if you are restricted to Pauli noise and stabilizer codes. But the minute you go to non-unitary channels, like the for any unitary channel, in fact for any channel which is a convex combination of unitaries, E-dagger will itself be the PETS map. Right? Because it is already physical. Yes. In fact, your E of P is just identity. So for any unital map, the PETS map is simply the adjoint map. But for a general channel, which is non-unital, like amplitude damping, again, which makes it a good candidate for this, is the,
But that is my query. Will it be for any unital or it is any random unitary? Because for qubit, I can see, okay, both are same set.
it doesn't matter. If your channel is unital, if you remember the PETs had this, so it's basically like this. So it's P.
Oh, you are saying because for unital I can.
This simply becomes identity.
The other way things adjoint
So
that we
it's
can
simply
define.
this. It's simply this. You don't need this
Yes.
to make the channel trace preserving.
So then, what is the process you are doing? Going to Stein-Sprain? Can you just repeat that?
Okay. So I'll have to find the. Maybe I'll just draw this and show it here. So, so I now want to implement this map R, right, with some set of Krauss operators. So I now have my, so I put a dash here to say that these are my encoded qubits, okay? And these are noisy encoded qubits. I now add additional ancillas, and I need as many ancillas typically as I have encoded qubits. And I just implement a large unitary, which I call V sub R, such that when I trace this out, what comes out here is, so this, what is input here is E of rho, because it's a noisy state, and what comes out here is this. That's it. And I mean, there are some tricks that we do to reduce the number of, so this large unitary, now you can sort of decompose it into smaller unitaries, and we come up with some tricks, clever tricks to decompose this efficiently. So that gives us the improvement in the circuit complexity.
Hi. So, is there any systematic way in which we can build this noisy codes? Like, do you start from CSS or something to come up with the superpositions, or?
So you're asking about a kind of ansatz for this, right? So, yeah, that's a good question. I don't know of a good ansatz for the encoding part, but what the PETs gives you is a good ansatz for the recovery. So in fact, one of the plots that I showed you with different 4-qubit codes, we fixed the recovery map to be the PETs map, and then you have to search over all possible encoding isometries of a particular dimension. Now you can use algebraic tricks like the Cartan decomposition and things like that to search for, but then the PETs need not be optimal, but if you get a good fidelity by fixing the recovery to be the PETs map, then that tells you that whatever you end up with as the final optimal recovery, it will only do better than that. So you can use the PETs as a good ansatz for the recovery and search for encoding processes. So yeah, we've done that.
And the second question I had is, supposing I have amplitude damping, but I sample the noise over all poly noises. And then I do the statistics of which poly noise is occurring most of the time, and I just correct those ones. Would that just give me a fidelity which is also appreciable, some kind of an approximate code or approximate PEP conditions?
So maybe what you're saying is along the lines of twirling, right? So you can twirl amplitude damping to make it into Pauli noise. But when you do that, you end up with actually a biased noise scenario. In fact, you'll end up with asymmetric depolarizing noise, where the Z noise is, I think, dominant. I forget, yeah. So there's some bias in that. And then you can do your stabilizer codes for that, right? Now, to me, yeah, as far as I know, the fidelity that you get is anyway still order gamma squared. So to me, that process seems expensive, much more expensive, compared to just using a 4-qubit code. Because you first have to implement twirling, and you need actually random unitaries to do the twirling, and then you end up with a Pauli noise channel, and then you're doing error correction, right? So that's a more expensive process, especially if you think about doing it on a hardware, than doing a 4-qubit code.
So without the twirling, I think the noise would not be appreciated.
So in this case, I don't think twirling really helps, because you're again going to end up with a depolarizing noise, and your fidelity is still gamma squared. So it doesn't matter whether you directly apply a 5-qubit code or you twirl it and apply, the linearity of the Knill-Leflam condition takes care of that in some sense.
Error correction code, no. So Warner has something, another extension. He calls it environment assisted error correction. So message is going to environment. Let's say some part of environment we have control on environment, we do the measurement and take the classical help. Because if we take the quantum help, then it is isometry unitary, no
yeah,
error is
yeah,
happening.
yeah.
Classical help. And there also he proved some interesting result. If you consider only this means qubit case, all unital, then you can perfectly error correct it. But for non-unital or this
Amplitude damping sort of,
that will
I
not
see.
work.
Okay, I was not aware of that, but yeah.
Whether there is some connection or not.
Yeah, I'd be interesting to see that. Yeah, I was not aware of that.
Okay, so if there are no further questions, let us thank both the speakers of this session. And do you want to say something?